I first thought of this problem when my family and I were camping in this little rental cabin, and it was really cold. It was 10 degrees Fahrenheit outside. And there was just a little 1500 watt heater that would keep the cabin warm, and I really worried that if that cabin failed during the night, it would get very cold inside the cabin. So I thought of a physics problem. Let's say that inside the cabin currently, with the heater on, it was 72 degrees Fahrenheit, nice room temperature. But I wanted to figure out how long it would take for the cabin to cool down to 20 degrees Fahrenheit when it was 10 degrees Fahrenheit outside. So this problem involves two big areas of thermodynamics. One is heat current. That how much heat goes in or out of an object depends on those variables. And we're talking about heat flowing through the walls of the cabin. So we have to use what's called the thermal conductivity coefficient for the material the walls are made out of, which is this yellow pine timber. And it has a coefficient of 0.147 watts per meter Celsius degree. Okay, and then the other variable that affects it is the total surface area of those walls and the difference in temperature. We're using delta here, but the difference in temperature is what we're referring to now, not necessarily the change in temperature. So the difference in temperature, if it's warm inside the cabin and cool outside the cabin, the bigger difference in temperature would create more heat current. And heat always flows from high temperature to low temperature. So if it's warm in the cabin and cooler outside, heat's going to go from warm to cool. The other way is also true. If it's really warm outside and cooler inside, heat is going to go from outside to inside. So the rate that happens is proportional to the difference in temperature. The other variable that affects it is the thickness of the walls. And it's inversely proportional because the thicker those walls are, the less heat is going to be passing through those walls every second. So that's heat current. The other thing is specific heat capacity. So if heat leaves air, how much is the temperature of that air going to change? And so Q is the quantity of heat that goes in or out of the air in the cabin. And it is related to how much mass that air has, the specific heat of air, and how much it changes its temperature. So an example would be like the specific heat of water. If I had 1 gram of water and it changed its temperature by 1 Celsius degree, because the specific heat of water is 1, it's going to take 1 calorie of heat to do that. If I had, say, 5 grams of water and I wanted to change its temperature by 3 degrees, 5 times 1 times 3, it would have taken 15 calories to do that. And we're not measuring calories, we're going to be measuring joules, but that is taken care of in the coefficient that we're using, or the specific heat that we're using, and I'm giving that right here in joules per kilogram Celsius degrees. And then lastly, this is the change in temperature as well. This is a change in temperature, this is a change in temperature, but this is the difference in temperature. So you have to be careful. And change in temperature is just the temperature initial subtracted from the temperature final. All right, let's see if we can do this. Let's go ahead and calculate how much heat is going to be leaving that cabin during the very first second after the heater turns off. So it's going to be a formula, and we're calculating heat current. So we have to use the coefficient of thermal conductivity. That's this number there. I'm hitting F4 on my keyboard. If you don't have an F4 on your keyboard, you have to just insert $signs. It's always going to refer back to that number. And then we're going to multiply that by the cross-sectional area, total surface area, which is that number. And I gave you the dimensions here, and maybe that was a little insulting for me to actually go ahead and calculate that for you. I'm sure you would have rather have done that yourself. You're certainly capable. But for sake of time, I guess I did it for you. And I hit dollar signs on that as well because it's going to always refer back to that number. So I took the thermal conductivity coefficient times the cross-sectional area. Now I need to multiply that by the difference in temperature. Currently, the air in the cabin was 22.2 degrees Celsius, 72 degrees Fahrenheit, and outside the temperature was 10 degrees, or negative 12 degrees Celsius. So I'm going to take that current temperature with no dollar signs, because I do want, as I copy that down, I do want that to change. And then I'm going to subtract from it a minus 12, which is just the same thing as adding 12. Okay, and that's going to be the difference in temperature from one side to the other. That's that term there. Now I just need to divide by the thickness of the walls, and the average thickness of those walls is this number here with dollar signs. And when I hit enter, the cell did not turn green, and that's because I wasn't careful with what direction the heat was flowing. And then here it says that it needs to be a negative number because the heat is leaving. So if I just take all that and take minus 1 times what we got, it'll just turn it into a negative. So in the first second, 1700 joules are going to be leaving that cabin. So if 1700 joules of heat leave the air in that cabin, how much is the temperature of that air going to change? So we just found that in the first second, 1705 joules of heat left the cabin. And I want to find out what the change in temperature of that is going to be. Well, it's just that 1700 divided by the mass of the air and the specific heat of the air would give me the change in temperature. And if I take the change in temperature and add to it the initial temperature, this term is going to come over here, it would tell me what my new temperature is. Okay? So we're going to say equals. I'm trying to calculate the change in temperature. So I have to take this number here. That was the heat current. That's how much heat left in 1 second. No dollar signs, because as I copy that down, I do want to use the numbers that are down. I want to figure out how much heat left it in the next second, and so on. All right. So that was the how much heat left. I need to divide it by the mass. Okay. Well, I didn't give you the mass of the air, but I did give you the density and the volume of the air. Density times volume would give you the mass. So I could use parentheses dividing by density times volume, or I could just divide by the density and divide again by the volume. I'm referring to numbers over here, so I have to put dollar signs here and dollar signs there, because I don't want it to refer down to different numbers as I copy it down. I always want it to refer to those numbers there. So all I've done so far is I've taken the heat current and I've divided it by the mass. Now I need to divide it by the specific heat of air. And the specific heat of air is this number there with dollar signs. So that divided by this would be the change in temperature. That's this number here, the change in temperature. This term over here, if I add to it the initial temperature, that will tell me what my final temperature is. So it started out at 22.2. 1 second later, it's 22.14 pretty much. So it dropped just a little bit in that first second. Okay. Now, that was a lot of calculations. But what we're going to do is we're going to copy that all the way down. This number refers to these over here, and that number. This number refers to those, and this number, and that number. But if I just select both of those numbers and copy it down, Okay, so I've just copied it down, say 100 times. Okay, and we've only cooled from 22.2 to 17.2, and we're trying to get to, let me come back up here, we're figuring out how long it's going to take to get to minus 6.67. So we have to copy it down further. All right, so let's just copy it down, copy it down. A lot of calculations are happening here. So we've copied it down 500 times, and now we're only the temperature inside the cabin is a positive 2 degrees Celsius. It's not quite even freezing yet. And we're trying to get minus 6.67. Okay. Well, now we're down, we've copied it down 817 times, and now we're at minus 3.7, but we still got to go down further. And let's see where we're at now. Okay, now it's at 4.7. Keep copying it down. Oh, now we passed it. Okay, so looks like, and the way I have my formatting here kind of tells you when you need to do it. But that's when it got to be, the first time it got to be negative 6.67 when we round up. The other thing I want to do is just figure out how many seconds that is. If I highlight both of those and copy them both at one time, the first number was 0, the next number is 1. When we copy two things like that, it knows that I'm trying to create a list of numbers that increase by 1. So we're getting there, almost down right there. It looks like it's going to take about 1,057 seconds to cool down to that temperature of minus 6.67. So the number of minutes is going to equal 1,057. That's, and my answer over there was in seconds. So if I divide by 60, it should get me into minutes. And there we go. It's going to take about 17.5 minutes for that cabin to cool down to that temperature. Next thing it says is to make a graph of the air temperature inside the cabin as a versus time. So I got to graph the air temperature in the cabin as a function of time. Maybe the easiest way to do that is to go ahead and highlight all three of those. So we're going to be graphing the heat current against time, but we'll delete that as we make our chart. So I'm copying down here, all the way down here. Give it a second. It's doing a lot of calculations. So right there it was. Okay. So I'm going to scroll back up so that when I put my chart there, I'm going to get more on the toolbar here by clicking down arrow. I'm going to insert a chart. There it is. Now the chart's funny here because we are graphing three things, and it defaulted to a line chart. We have to change it into a scatter plot, and this is something that can trip you up, but mine was already checked. Use column A as labels. So that's essentially saying that column A is your x-axis. Okay, so if that's not checked, make sure that it is checked. Now we have too many things here. It's this column B that we don't want here, and here is column B. So I'm just going to go ahead and then remove that one, and there, that looks a lot better. So over the course of a little more than 1,000 seconds, it cooled from 22.2 degrees Celsius all the way down here to about minus 6.67 degrees Celsius. And I'm just going to put that in this little space here and clean it up a little bit. There we go. Background won't turn green on you this time. I'm going to leave these two questions for you, but as often in physics, we set up a problem and find out that we best use the variables that we were aware of, but sometimes there's other variables that we weren't accounting for. So two things. What assumptions were made that might not necessarily be valid, and what are some other variables that were not accounted for? So type your answers there. It's not grading it to see if you got it correct, but something for you to think about. Okay, that is heat current in combination with specific heat, and quite a useful problem.